Hello everyone, this video is on group 15 elements for visual impaired students. Introduction. Group 15 element of the extended or long form of periodic table contains 5 elements, namely nitrogen, phosphorus, arsenic, antimony and bismuth. This group is also known as nitrogen group. All the elements of this group belongs to p block due to the filling of p orbitals of the valence shell by the last electron of the atoms of these elements. The first two elements, nitrogen and phosphorus, are distinctly non. The next two elements, arsenic and antimony, are semi-metals, and the last element, bismuth, is metallic in nature. These elements, except phosphorus, do not occur very abundantly in nature. Nitrogen constitutes only about 0.0054%, phosphorus 0.116%, antimony bismuth nearly 10 raised to power minus 4% of the rocks of earth. The phosphorus ranks 10th in abundance among all the elements known. Nitrogen constitutes nearly 78% by volume of the atmosphere. General characteristics. The inclusion of nitrogen group elements in the same group of modern periodic table is justified by the following several characteristics of these elements. These elements furnish another example in which there is a systematic gradation of properties and there is a change of character from a true non-metal like nitrogen to a nearly true metal, example bismuth. Electronic configuration of group 15. There are 5 electrons in the valence or ultimate shell of the atoms of these elements, that is ns2p3, where n is the principal quantum number of the valence shell. Two of these electrons are in the s subshell and the rest three are occupying the p subshell according to the Hund's rule among the three p orbitals. Because of exactly half-filled orbitals, the elements are fairly stable and not so reactive. The penultimate shells have variation in the number of electrons. The first elements, nitrogen, has helium configuration S2, P has inert gas octet S2P6, and other elements have pseudo inert gas S2P6D10 configurations, respectively in the penultimate shells of their atoms. This variation in the configuration is responsible for gradation of properties in the group. Occurrence. Nitrogen occurs in the free state as the diatomic gas in nature, while all the remaining elements occur in the combined state. In the combined state, it occurs mainly as nitrates. Being very reactive, phosphorus does not occur in the native state. Rather, it occurs as phosphates in its ores. Antimony, bismuth are less abundant and occur chiefly as sulfide ores. The next topic is physical state and element structure of group 15 element. Nitrogen is a gas, phosphorus is soft, lustrous, less solid, other are hard solid. Antimony and bismuth having characteristic metallic luster. Nitrogen has exist as a diatomic molecule, N2, while phosphorus, antimony, arsenic, bismuth exist as tetraatomic molecules. P4, As4, and Sb4. These are not capable of forming diatomic molecules like N2 because they do not form pi bonds as their larger atoms cannot come closer to each other to form such bonds as well as P has inert gas octet S2P6 and other elements have pseudo-inert gas S2P6 D10 configurations respectively in the penultimate shells of their atoms. This variation in the configuration is responsible for gradation of properties in the group. Occurrence of 15th group element. Nitrogen occur in the free state as the diatomic gas in nature, while all the remaining elements occur in the combined state. In the combined state, it occurs mainly as nitrates. Being very reactive, phosphorus does not occur in the native state. Rather, it occurs as phosphates in its ores. Antimony, bismuth, arsenic are less abundant and occur chiefly as sulfide ores. Physical state and elemental structure. Nitrogen is gas, phosphorus is soft, lusterless solid, others are hard solids. Antimony and bismuth having characteristic metallic luster. Nitrogen gas exists as a diatomic molecule N2, while phosphorus, arsenic, and antimony exist as tetraatomic molecules P4, As4, and Sb4. These are not capable of forming diatomic molecules like N2 because they do not form pi bonds as their larger atom cannot come closer to each other to form such bonds as well as due to the increased repulsions from the non-bonding electrons of penultimate shell. The repulsion from the electrons of penultimate shell 1s2 in nitrogen atom is not appreciable. Further formation of pi bond in the N2 molecule satisfy the valency requirement of N atoms, while non-formation of such bonds in their element compels them to join with other more atom. Hence M4 molecule are formed. These elements thus form giant lattices in which the bonding changing from covalent to metallic from phosphorus to bismuth. Now we will discuss about metallic and non-metallic character. The change from non-metallic to metallic character with increasing atomic number in the same group existed by group 14 is observed equally well in this group also. The only metallic element being bismuth, the last element of the family which has the lowest value of ionization energy. This is revealed by the variation in the properties both physical and chemical. Density, hardness, atomic radius and atomic volume. On going from phosphorus to bismuth, these properties increase regularly and markedly. The atomic radius and atomic volume also increase down the group with the expectations of atomic volume of arsenic which has low value. ionization energy, electronegativity, and heat atomization. With increasing size from nitrogen to the values of first ionization energies decrease on descending the group. Similar is the trend in the electronegativity and heat of atomization. This gradation confirms the gradual increasing metallic character of the elements. Now we will discuss about melting and boiling points. The melting point and the boiling point both increase with increasing atomic number. The melting point of bismuth is unusually low, perhaps because of non-availability of N2 electron pair for bonding in the metallic crystal. The elements of this group are more volatile than their immediate neighbor of group 14. Oxidation states. First, formation of M5 positive and M3 positive cations. M5 positive cations are formed when all the valence electrons Ns2 P3 are used by the elements for bonding. Nitrogen and phosphorus cannot lose all the 5 valence electrons due to prohibited energy considerations. That is because they have high ionization energies and electronegativities and hence do not form M5 positive ions. These elements also do not form M3 positive ions as such, but these oxidation states, that is plus 3 and plus 5, can be assigned to them arbitrarily in their compounds with more electronegative elements. Oxygen and fluorine is formed. M3 positive cations are formed by the elements if they lose only p electron from Ns2 P3 configuration of the valence shell and Ns2 electron pair remains inert. Since this effect increases down the group, the heavier element antimony and bismuth are expected to form M3 positive ions by losing 3p electrons only and retaining the Ns2 electron pair, though they can form M5 positive ions as well. Thus, only arsenic and antimony will give salt with plus 5 and plus 3 oxidation states, and bismuth gives only Bi3 positive ions. Now we will discuss about formation of M3 negative anions. In order to achieve noble gas configuration, these elements accept 3 electrons from electropositive elements and form M3 negative ions. Example, nitrogen in ammonia has -3 oxidation state. As the size of the atom increases on moving down the group, the ionization energy and electronegativity values decrease, and hence the attraction of the nucleus for the newly added electron decreases. Thus, the tendency of the elements to give M3 ions also decreases. In fact, an atom being smallest in size has strongest tendency to form M3 ion. P form P3 negative ions less readily, and bismuth, the last member of the group, hardly exhibits negative oxidation state. Covalency of 3 and 5. Each of these elements has two paired s electrons and three unpaired p electrons in the valence shell. If these elements form three covalent bonds using only the p electrons, they attain the noble gas configuration Ns2p6. This gives the covalency of 3 to these elements. Except nitrogen, these elements also have vacant d orbital in the valence shell. Under suitable conditions of energy, one of the electrons of s level may be promoted to the vacant d orbital, thus possessing 5 unpaired electrons. These 5 unpaired electrons may be used to form 5 covalent bonds, thereby giving the covalency of 5 to these elements. This covalency is common among phosphorus, arsenic, and antimony. That is why nitrogen forms only trihalide and other elements form tri as well as pentahalide. Electron donor acceptor properties. All the elements in the trivalent state have a tendency to act as electron pair donors. Nitrogen having this tendency to the maximum extent. For example, NH3 and PH3 molecules act as Lewis bases toward H positive to form NH4 positive, PH4 positive, etc. Due to the presence of lone pair of electron on nitrogen and phosphorus atoms, thereby nitrogen showing a maximum covalency of 4, phosphorus, arsenic, and antimony show a covalency of 6 in PCl6, AsF6 negative, and SbF6 negative complex ions in which their salts act as electron pair acceptor. Allotropy. All the elements except bismuth show allotropy. Nitrogen in solid state exists in two allotropic forms, alpha nitrogen and beta nitrogen. Phosphorus exists in various forms such as white, red, scarlet, alpha black, beta black, and violet. Arsenic exists in gray, yellow, and black allotropic forms, while antimony in the form as yellow, black, beta, and explosive. Catenation, self-linkage. Although the catenation is considered to be a property peculiar to carbon, yet it is shown to some extent by the element lying close to carbon in the periodic table. The elements of this group have been found to show this property, but to a much smaller extent than carbon. Thus, unstable compounds containing chains of up to 8 nitrogen atoms have been prepared, but stable azide ion has a chain of 3 nitrogen atoms, that is N negative skeleton, and NH2 has 2 N atoms. In case of phosphorus, p bond p links are limited to 2 atoms. Other elements of the group have no tendency of self-linkage. Thus, tendency of catenation decreases on moving down the group because of gradual decrease in bond energies of metal-metal bonds. Electrical and thermal conductivity. Both these properties increase as we move down the group because of increased delocalization of electron from nitrogen to bismuth. Thus, nitrogen and phosphorus are non-conductor. Arsenic is a poor conductor. Antimony is a good conductor, and bismuth is an excellent conductor. Combination with active metals. All these elements form compound with metal. Example nitrogen form nitrides, Lin, Mg3N2, etc. Phosphorus form phosphide, Ca3P2, etc. Arsenic gives arsenides, Na3As, etc. Antimony gives antimonides Mg3Sb2 and bismuth form bismuthides M3 Mg3 Bi2 etc. The nitrides among these compounds are most stable. The last two types of compounds are rare and antimony and bismuth in fact form alloys on combining with metals. Chemical reactivity. These elements differ from one another appreciable in their chemical reactivity. Nitrogen is chemically non-reactive. It does not combine under ordinary conditions. It combines with elements such as lithium, aluminium, calcium, magnesium, etc. to form nitrides at high temperature only and combine with oxygen only when heated in an electric arc to a temperature of the order of 15 2500 degrees Celsius and above forming nitric oxide. On the other hand, white phosphorus, an allotropic form of phosphorus, is extremely reactive. It burns readily in oxygen, forming oxides of phosphorus. The heavier element arsenic, antimony, bismuth burn only when heated in air or oxygen to form oxides. This can be attributed largely to difference in the electronegativities of the five elements. Now we will discuss about uses. First, nitrogen is an essential element for the growth of plants. It is generally added to the soil in the form of fertilizers or atmospheric nitrogen is fixed by nature and this is absorbed by soil. From the soil it goes to the plants and then to the animals. Second, red variety of phosphorus being non-poisonous is mostly used in match industry. Third, phosphorus is also used as rat poison and in the manufacture of tracer bullets as well as in producing smoke screens. Fourth, antimony and lead alloy is used in making lead shots. Fifth, antimony is mainly used in the manufacture of lead storage batteries as it is harder and acid resistance. Sixth, bismuth alloys have low melting points and are called fusible alloys. These are used in making automatic electrical fuses, fire alarms, sprinklers, safety plugs on boiler, etc.